Chapter 6 is all about normal probability distributions, and we begin with this lecture on the standard normal distribution. If a continuous random variable has a distribution with a graph that is symmetric and bell-shaped and can be described by the following equation, we say it has a normal distribution. No need to worry, we won't be using this equation. But the graph of that equation is in fact this normal distribution, with mu as the mean and sigma as the standard deviation. We are also interested in what's called a uniform distribution. A continuous random variable has a uniform distribution if its values are spread evenly over the range of possibilities. The graph then results in a rectangular shape, just like you see pictured here. Notice that for each x value, the probability is exactly the same. We have the same height for the graph across the entire range of possibilities. These are both examples of continuous probability distributions like we've been working with, and their graphs are examples of density curves. We have the following properties. The area under the graph of a continuous probability distribution is equal to 1. There's a correspondence between area and probability. So probability can be found by identifying the corresponding area in the graph. The most important idea in this lecture is that there is a correspondence between area and probability. The area under the curve is the probability for those values. Let's take a look at an example. The amount of voltage into a building is uniformly distributed between 130 and 135 volts. That means that any voltage amount between 130 and 135 is possible, and all values are equally likely. Let's find the probability that a particular voltage is greater than 132. Let's start by drawing the density curve that goes with the situation. We are told that the voltage is uniformly distributed, so along the horizontal axis, we'll label our x values, or voltage. We know that they can range from 130 to 135. And since all of these values are equally likely, they all have the same probability. We're not told exactly what that probability is, but whatever it is, it's the same all the way across, so our density curve takes on the shape of a rectangle. We also know that the total area of this rectangle has to equal 1. The area of a rectangle is equal to its width times its height. In this situation, we have an area equal to 1 and a width equal to 5, but we don't know the height. Dividing both sides of this equation by 5, we find that the height is equal to 1 over 5, or 0.2. That means that this uniform probability across the range of values is equal to 0.2, or 20%. Now, let's find the probability that a particular voltage is greater than 132. That is, we want to be to the right of this line. Since there's a correspondence between area and probability, to find the probability of the voltage being to the right of this line is the same thing as finding the area of the rectangle to the right of this line. That is, we want to find the area of this rectangle with width equal to 3 and height equal to 0.2. That's an area of 0.60. In other words, the probability of the voltage being greater than 132 is equal to 3 times 0.2, or 0.6. The standard normal distribution is a special case of a normal distribution. This is a normal distribution where the mean is equal to 0 and the standard deviation is exactly 1. That is, our normal curve is centered on a value of 0, and 1 standard deviation above the mean would be 1, 2 standard deviations above the mean would be 2. 1 standard deviation below the mean would be -1, and 2 standard deviations below the mean is -2. Let's take a look at this example. The average temperature in a northern town is 0 degrees Celsius with a standard deviation of 1 degree Celsius. We're going to assume that these readings are normally distributed. Notice that we've already been given that the mean is 0 and the standard deviation is 1. So this is an example of a standard normal distribution. Let's find the probability that at a given point in time, the temperature is less than -2 degrees Celsius. We'll start with our picture with a mean of 0 and a standard deviation of 1. -2 degrees Celsius is 2 standard deviations below the mean, and finding the probability that a given temperature is less than -2 degrees Celsius is equivalent to finding the area under the curve to the left of -2. Now, one important feature of a standard normal distribution is that since the mean is 0 and the standard deviation is 1, each x value corresponds to its own z-score. A data value of 1 is one standard deviation above the mean, so it has a z-score of 1. And so on. So the area under the curve to the left of -2 is equal to the probability of having a z-score that's less than -2. There are two ways that we can find this area. This is what a z-table looks like. The first row and first column correspond to a particular z-score. In the first column, we have the z-score given to one decimal place, or the tenths place. In the first row, you find that second decimal place for the z-score, or the hundredths place. And in the center of the table, you have the corresponding area to the left of that z-score. In our example, we're interested in a z-score of -2. So let's take a look at the z-table corresponding to negative z-scores. Going down that first column, we can find -2.0. And since we want -2.00, we only want to go over one column, where the hundredths place is also 0. Where these two meet, we find a left area of 0.0228. That means that the area under the curve to the left of a z-score of -2 is 0.0228. And because we know the area, we know the probability of the temperature being less than -2. We can also find the area under the curve using our calculator. In order to use our calculators to find the area under a normal curve, we go to the DISTR menu by pressing second vars and toggle down to normal CDF. Pressing enter for this type of calculator brings up the normal CDF menu, where you can enter the lower and upper range. We want the area all the way to the left, which goes on to -infinity, but we can't enter a lower value of -infinity, so instead we'll put a very large negative number to represent -infinity. And in our example, we have an upper limit of -2. We leave our mean at 0 and standard deviation at 1, and once paste is highlighted, we can press enter to take that back to our home screen. Pressing enter again gives us a left area of 0.0228, the same value that we got using our z-table. If you have a different type of TI calculator, normal CDF may not bring up the menu to enter the lower and upper limits. Instead, you might see something like this. And you'll need to enter the lower limit, upper limit, mean, and standard deviation in that order separated by commas. Then press enter for the corresponding area under the curve. Now let's find the probability that the temperature will be greater than 1.57 degrees Celsius. We will start again with our picture of our standard normal distribution with a mean of 0 and a standard deviation of 1. This time we're interested in temperatures that are greater than 1.57. That is 1.57 standard deviations above the mean, and we can sketch that value here. To find the probability that the temperature will be greater than this value, we need the area under the curve to the right of this value. This area is equal to the probability of having a data value greater than 1.57. Let's first look at our z-table to find this area. This time our z-score is positive 1.75. So we'll look at the part of the table that deals with positive z-scores. To find 1.57, we go down the first column to 1.5 and go across to 0.07. Where these two meet, we have the area to the left of that z-score. It's really important to note that no matter if we're looking at positive or negative z-scores, the z-table always gives us areas to the left of the z-score. So here we have a left area of 0.9418. And if the area to the left of 1.57 is 0.9418, then the area to the right is equal to 1 minus 0.9418. 1 minus the left area, which gives us an area of 0.0582. That is, the probability of having our data value, or temperature in this case, be greater than 1.57 degrees Celsius is equal to 0.0582, or just under 6%. In order to find this value using our calculator, we can go to the DISTR menu, toggle to normal CDF, and enter our lower and upper bounds. Since our area begins at 1.57, that's our lower bound. And since the area goes on forever to the right, we'll enter a really large number. Notice that this won't be exact, but it will be enough accuracy for our purposes. Pasting this, we find an area under the curve of 0.0582, which is exactly what we got from our table. Finally, let's find the probability that the temperature will be between -2.1 and 1.07 degrees Celsius. On our picture, this is the area under the curve between -2.1 and 1.07. Let's first go to our z-table and find the corresponding areas for our z-scores of -2.1 and 1.07. -2.1 is -2.10, which we find has a left area of 0.0179. Looking at our table for positive z-scores, we find that a z-score of 1.07 has a left area of 0.8577. So the area between these values is equal to the larger area, 0.8577, minus the area in that left tail, 0.0179, because we don't want to include that left tail. This gives us an area between these two z-scores of 0.8398. That is, the probability of the temperature being between -2.1 and 1.07 is equal to 0.8398. Let's run this through our calculator. Using the normal CDF function on our calculators, we have a lower limit this time of -2.1 and an upper limit of 1.07. Leaving our mean at 0 and standard deviation at 1, we can paste this into our main window, and pressing enter gives us an area of 0.8398, the same value that we just got using our table. Now let's consider this example. We have a company that makes thermometers and they're testing the accuracy of each one. After being dipped in water, each one is supposed to read 0 degrees Celsius, the temperature of the water. The average of the readings is 0 degrees Celsius, that is, the mean is equal to 0, and the standard deviation is equal to 1 degree Celsius, that is, sigma is equal to 1. We're going to also assume that the readings are normally distributed, and given that we have a mean of 0 and a standard deviation of 1, we know that this is a standard normal distribution. We're going to find the temperature that separates the bottom 5% from the top 95%. That's the equivalent of finding the 5th percentile. Let's start with our picture. We don't know exactly where the 5th percentile is yet, but we do know that it's pretty far over to the left, so I'll just sketch it here. Since we're looking for this temperature value that separates the bottom 5% from the top 95%, we actually do not know the z-score this time, but we're looking for it. What we do know is that the area to the left is equal to 5% or 0.05, and the area to the right is 95% or 0.95. Recall that probability corresponds to area under the curve. So we're looking for the z-score that has a left area of 0.05. Let's take a look at our z-table. Since we are to the left of center, we are looking for a negative z-score, and we need a left area of 0.05. So we need to find the value in the center of the table that's the closest to 0.05. Look at these two areas here. 0.05 is exactly in between these two numbers. These areas correspond to z-scores of -1.64 and -1.65. Since the area that we're looking for is precisely in the center of these two areas, the z-score that we are looking for is precisely in the center of these two z-scores. That is, the z-score we are looking for is -1.645. This threshold of 5% or the 5th percentile is pretty common, so you might want to make a note of it on your z-table if the version of your z-table doesn't already have it. Now let's find the temperature that separates the bottom 95% from the top 5%. That's the 95th percentile. This is the value that has a right area corresponding to a probability of 5% or 0.05, and a left area corresponding to a probability of 95% or 0.95. So we're looking for a z-score that has a left area of 0.95. Let's head back to our table. This time, since our score is to the right of center, we know we need a positive z-score. And looking at our table of positive z-scores, we want to find the area that's as close to 0.95 as possible. Again, we find that 0.95 is exactly in the center between two given areas. These two areas correspond to z-scores of 1.64 and 1.65. So the z-score that we want is right in the middle of those two, or 1.645. That is, this time our z-score is positive 1.645. Notice the symmetry that we have here. The 5th percentile is negative 1.645, and the 95th percentile is positive 1.645. This comes from the fact that normal distributions are symmetrical. We expect that the values on one side of the curve are a mirror image of the other side of the curve. We can also find these values using our calculator. We start by getting into the DISTR menu and toggle down to INV norm. This time we are asked to enter the area rather than the left and right limits. For part A, we were interested in having a left area of 0.05. So let's enter 0.05 for area. We have a mean of 0, a standard deviation of 1, and we're interested in this 0.05 area being to the left of our value. This then gives us a z-score of negative 1.645, which is exactly what we found using our table of values. For part B, we again will start in the INV norm menu, and we can enter either a left area of 0.95 or a right area of 0.05. Since I already have 0.05 for my area, I'm just going to switch this to the right tail rather than the left. And pasting this and pressing enter, we have a z-score of positive 1.645. Again, if you're using a different calculator, you'll need to enter these values in the correct order, separated by commas. Now we know how to go from area to z-score and z-score to area. The most important idea of this lecture video is the idea of that correspondence between area and probability. That concludes this lecture video on the standard normal distribution.